David? Oh, yeah. I was gonna. I got the email. Is that like inside the quiz, or is it like separate? Okay. So like it would just be like question, and then there's like a mouse thing you could just click like upload or something. I'm guessing it has to be PDF, right? Like not any other. I think PDF would be best. I mean, like otherwise they upload some weird like dot whatever, and like we need a different app to like open it. Okay, cool. Oh yeah, I'll tell the class. Thanks, David. Okay. So in case you didn't know, David was the other TA. Um, so your quiz, um like the weekly quiz, not like the lecture quiz, it will have one of the questions you will have to like upload. Like, you write it down on paper and then you just upload it as a PDF. Yeah, so it'll be like a written answer. Yeah, so just make sure before you start the quiz to like, get your writing tools or whatever before you start it. And I think it's best to upload as PDF. Yeah, if you can. No. So both sections take the same quiz. Yeah. So like you're not doing it like it's not like a different one for every section. It's just that we take turns like making it, and same for like yeah. So we take turns doing it like every week. Although a lot of the times I think the professor just made them and then we just release it. So we don't really have a say for quiz questions most of the time. But like I do look at it, so I try to cover everything you need for it. So don't worry about that. Okay, let's get started. Um so let's talk about rings. So last time I went over groups, right? Like hopefully you all know, like I went over groups like integers under plus, right? Rational numbers. But a lot of times, right? Like in the and like real numbers, like you it's not just like one operation on it, right? Like you can add integers and you could also multiply them. So there should be a notion of an object where you could have, do like two operations, right? Add and multiply, right? So a ring, it's a set with two operations now. So no, this is just notation, right? Like this is, think you should think of it as plus and times, right? But this is just a notation for the operation. Is a set R with binary operations plus and times, where I'll just do R1 for like axiom 1, right? R under plus is a abelian group. Can anyone remind me, just a quiz, mini question, what does abelian mean?
It means it's commutative.
Yeah, it commutes, yeah. And then R2, so this is for plus, right? That's pretty much, tells me everything, right? So in other words, it satisfies like the three group axioms, right? For this is for plus. Now for times, right? We sort of want integers, to be a ring too, right? So what you're gonna notice is okay, instead of writing this, let me just put star as associative. Yeah. So multiplication satisfies the associativity property. And R3, right? This is for plus and this is for times, right? You see, right now we don't really know how plus and times communicate with each other, right? So think of this as like a way plus and multiply communicate with each other. Like how do they interact with each other? Communicate. And it's through the, hopefully you all know this, but it's called the distributive property, right? So A times B plus C. What is that? It's A times B plus A times C. Yeah. And then A plus B times C is A times C. And no, I'm not changing the order. Yeah. So I'm not writing C times A for the second one. Because one thing you note is that like multiply need not be commutative, right? Because we want like the set of matrices to be a ring, right? And as you know, matrices don't commute under multiplication. And similarly, you see in some books require this, but no need for identity. By the way, we call identity for under plus identity under plus. I'll just put plus as 0. Yeah, this is just notation, right? But some books, like if there is, we denote it as 1. Yeah, because when you think of, if you think of this dot as multiply, right, the identity element is 1, right? And you see here there's no need for inverses. Like by no need I mean there's no requirement. Like it could have inverse, but it couldn't. So here, right, this makes Z into a ring. Do you all see that? Because we don't need like a half, right? Due to like this thing right here, they don't require inverses. So this is a ring, right? Is everyone good with that? Like, because if you required inverses, then what's the inverse of 2 under multiplication? It's a half, right? But a half is not an integer. so yeah, so examples would be, let me just continue. Right, z under plus and times, right? Let me just to make it quick, there's also q, r, same exact operations, complex numbers, right? And then z mod nz. Right, and then you have like matrices, right? And then this doesn't really matter, but yeah. Okay, so is everyone clear with this? Yeah? Yes, no? Okay. So from here, right, before I continue, like the book proves a lot of properties, like let me just say properties you think are trivial. But it's really not. So let me just, convince you why they're doing this. When you read the book, you're like, why on earth are they even doing this? Like sometimes they prove something like this. Negative a times b, or not negative a. Let's just call it, this is just in notation, but is negative ab. Yeah. So like you would say this is dumb because this is like negative 1 times a. No, because you would think this, right? And then associativity gives this, which is this, right? But let me ask you, in the definition of ring, what is negative 1? Like, have just from here, do you know what the 1 is? You don't, right? Like, what do we mean by minus a? When the book writes minus a, where do we get that? That's just notation for what? So, like for example, minus a is notation for, it's just notation for element such that, I'll put s dot t dot for such that a, because it's a group under plus, right? So a plus minus a is the identity. Yeah. So it's just the thing where if you add it to a, you get the identity. Yeah. So that's what it is. So really what you're trying to prove is inverse of a under plus times b is inverse of ab under plus. Yeah, because this I know just from like here, right? Of course, if you think of your ring R as like, integers, you'll see that, minus is just minus 1 times whatever, right? But you see, the book is trying to generalize, right? Because your ring might not be integers, right? It could be matrices or something. So they have to prove it just from these axioms. Is everyone clear on that? So they do tons of like property proving here, but hopefully like you see why like they're doing it, because a priori, just from how we define a ring, like these properties might not, it's not obvious. So okay, so let me just go over what Cartesian product is. Cartesian product, right? right? As a set, it's just, you know, you take products of R1 cross R2 cross Rn, right? So where, let's just say it's Cartesian product of rings, so Ri is ring for all I. So as a set, this is just a set of, you know, R1, Rn, where Ri, you know, each, like R1 belongs to capital R1 and R2 belongs to capital R2. Yeah. So as a set, hopefully you know what, you know, a product is, right? But if each of these are rings, right? So if each of these is Ri, you know, if they're rings, so it's, I put plus sub I and dot sub I, you know, because they might have different, the operation might be different, right, for each ring. Then this becomes a ring. So yeah, where the operation is component wise. Yeah. So instead of just writing what this is, I'll just write how you do it. So R1 to Rn plus, I don't know, S, let's call it S1. So we have plus and times. So how do you add S1 to Sn? It's component wise. So this is R1 plus 1 S1, R2 plus 2 S2. Yeah. And then Rn plus n Sn. Right. So component wise. So and this makes sense, right? Component wise, because each ring has a plus, right? So here you're adding, this is in R1, right? Here you're adding in R2, so on and so forth. And then multiply is the same thing. I don't know why I just put that. I'll just put star 1 dot 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 Rn star n Sn. Yeah. Is everyone clear with this? So question, Ren, if each Ri, so if each Ri, so let me just ask you, why is this thing R1 cross R2 cross Rn an abelian group? Right. So to be a ring, it has to be in an abelian group under plus, right? So why is it abelian? So the fact that it's a group is pretty clear, but why is it abelian? Can everyone follow? Yeah. Yeah. Not. Yeah. Addition. Well, it's commutative on each ring, right? And you're doing everything component wise, right? So it's abelian because it's abelian on R1. It's abelian on R2 because I told you they are rings. And then it's abelian on Rn, right? So you see, it's abelian because each component you're in is abelian. So yeah, okay, good. So let's move on. So let me just say, Ren star is commutative, right? Because it might not be, right? From the how we define a ring, we say R is commutative ring. If yeah, because commutative ring. Yeah, we because if it's times, we normally don't say abelian ring. Yeah, the standard language is commutative for like a ring. because you don't want to confuse with like, for abelian, we tend to think of as just for groups. So, okay. With that in mind, let's continue. So now I'm gonna go over ring homomorphisms because I think some of your quizzes have a lot of questions on like homomorphism of rings and groups. So I went over what a group homomorphism was, right? So let's go over what a ring is. So let's call it phi from where, you know, R prime are rings. Yeah. So a map between rings, what is that, right? So given A, B, and R, right, it must respect the addition property, right? Right, because if it's just a function, right, if you just think of these as sets, right, then any function, any function you define, as long as it's a function, it will do, right? But a ring is more than just a set, right? It's a set with two operations. So your function should respect those operations. So in other words, if I add, so I'm not gonna confuse this, but phi of A plus phi of B. Yeah, I should be putting, so let me just say this is addition in R, right? And right here, it's addition in R prime. Yeah, because phi of A is in R prime, phi of B. So, you know, just keep in mind, you know, the plus, this is the plus in R, and this is the plus in R prime. And similarly, right, phi of AB is, it must respect the multiplication binary operation. So phi of A times phi, if you like, times phi of B. So again, this is times in R, and this is times in R prime. And then what is isomorphism? It's homomorphism. So let me just say ring isomorphism is a ring homomorphism plus it's bijective, yeah. Okay. Does everyone follow so far? So if you remember groups, it was just this, right? Groups was just because groups is one operation, right? But for rings, there are two operations. So there's two properties. Everyone clear? Yes? Okay. So let me just define this. We won't really be using it for now, but the kernel. So this should be fairly, you should know what this is. I mean, in linear algebra, what was the kernel? What's the kernel? Or like, if you like null space. Like, what is null space of a matrix, or like kernel of a matrix? Like, it's the set of things that satisfy like AX is 0, right? If you remember correctly, right? It's the set of things that map to 0. So kernel is just the set of A in my domain such that phi of A is 0, right? So this is again the identity under plus, and it's plus of R prime, right? Because this phi of A is in R prime. So make sure you know where you are in your domain and range. Okay, so from here, let's do some examples. Yeah. So let me just ask a question. So let's let phi be a map from Z to Z. I'm telling you it's a ring homomorphism. So let me just say if phi of 8 is 16. Ooh, actually, let me stop this for now. Let me go one more thing. here's a question. Must phi of 0 be 0? Yes or no? So this is 0 in R, right? This is 0 in R prime. So again, phi takes R to R prime ring homomorphism. So does this have to be true? Must you map the additive identity to the additive identity? So this is the first case where we practice this rule. Yeah. Like phi of A plus B is phi of A plus phi of B. So the first case would be if R was just 0, right? If the ring was just a 0 set, then just the element 0, then you're done. So basically, you choose a non-zero element, right? Or if you like, you just choose 0 if you want. So phi of 0 plus 0, what is that? From this rule, this is phi of 0 plus phi of 0, right? But what's phi of 0? This is phi 0 plus 0 is just 0, yeah? So this is phi of 0. So you have phi of 0 equals phi of 0 plus phi of 0. So you could, so note when I write subtract, right, it means add the inverse, yeah? So to be more concise. So this is the inverse is just 0, right? So this is 0 in R prime. Yeah. Is everyone clear on this? So whenever you have a ring homomorphism, you must map the what do you call it? Yeah, the additive identity to the additive identity of the other ring. So this is just, I just want to show this just to demonstrate how, this rule comes into play. Okay, now let's go to the actual question. Let phi be from z to z. So this is from integers to integers, right? Be ring homomorphism. So normally if they don't write, the binary operations, it's sort of implied it's this, right? It's the actual plus and actual times. So the question is, let's work with this. If phi of 8 is 16, what is phi of minus 8? Anyone? So let me start you. Yeah. Why? So let's start from here, right? 0 is phi of 0. Yeah. But phi of 0, what's 0? 0 is just 8 plus minus 8, right? No, yeah, I'm sort of proving that. Yeah, I mean, of course, if you could just take out the minus sign, but I'm working, just from this being a ring homomorphism, right? You sort of start from scratch, right? But yeah, if you know that rule, but I'm sort of showing that rule, right? So here, right, let's use the fact that I could split this up, right? So I'm using this rule now. I could split it up, right? My A is 8 and my B is minus 8. So I have 0 equals phi of 8 is 16. So hopefully you add negative 16 on both sides. You're going to get. Everyone clear on this? Yeah. So, being able to work with these stuff is pretty important. So let's continue. Let's do a continuation of the question still. So I'm gonna rewrite it from Z to Z ring homomorphism. Okay, so let me just say if phi of 8 is 16, phi of 4 is 8. What is phi of 2? So here I'm giving you practice on this rule now. Phi of AB is phi of A, phi of B. So use this. Yeah. So, right, because phi of 8 on one hand, it's 16, right? I mean, it's given here. But on the other hand, what is 8? 8 is 2 times 4, right? Now, using this rule right here, this is phi of 2, phi of 4. Now, phi of 4 is 8, so this is 8 times phi of 2. And hopefully, phi of 2 is 2. Okay, everyone clear so far? By the way, right, for a group homomorphism, right? Group homomorphism, like if I just, right, the same thing holds, right? So if I have G to G prime, I must map 0 to 0, right? The 0, the identity of the group, or if you like, some books call it E to E. Yeah, it's the same proof as I did before, right? Phi of E plus E is phi of E plus phi of E, right? So let's be more clear here. Yeah, so the plus could be different, right? This is like the plus of G prime, the plus of G plus. And then you subtract, right? This is just phi of E. And then you get 0, or E equals phi of E. Yeah. Is everyone clear on this? So the mapping identity to identity, that's true for groups and rings. Yeah. Because if you notice for the proof of my ring one, I only use the plus, right? I never use anything with multiply. so yeah. Okay. Now what I want to go over is cyclic groups. So these are groups generated by one element. So you'll see why it's important for your like quiz or something, because it's going to ask you like on homomorphisms, and you'll see everything's determined by where you send the gener. So groups generated by one element. Yeah. So an example, Z, it's generated by 1. You could also say it's generated by -1 if you like, or. So why is Z generated by 1? Well, if I just start with 1, I know it's a group, right? So I can add, right? So I can add 1 to get 2, right? So any positive number like n, I can get that, right? Just by adding like 1 n times. Do you all agree? Now, I know if Z is a group, it must have an inverse, right? So the inverse is -1, right? So equals inverse of 1. So 1. And then, so now I can get every negative number by just taking the inverse of 1 and then adding it, right? So -1 n times. What you're going to see is you're going to get all the integers, right? So basically, this means, so like, let me just say, by taking powers of 1 informally, taking, powers of 1. So by powers of 1, I mean like, 1 squared is 1 star 1. This is the group operation. Yeah. So this is, in this case, the group operation is plus, so it's 2, right? So this thing generates all of z, right? Because you have 1 inverse, 1 of the 0. In fact, 1 of the 0 and 1 of the 1 is the same thing. 1 of the 2, this is 2. Like 1 to the 3, this is 3. The inverse of 1 is -1. And then, so on and so forth, right? 1, -2, this is -2, ... So you see, in a sense, 1 generates the whole group. So when that happens, when your group is generated by like 1 element, it's called cyclic. Okay, do you all see that? Yes or no? Need to. Okay. So hopefully you all see that Z mod NZ is cyclic, right? What is this generated by? Not a trick question. This is the set of 0, 1 to n minus 1. Yeah, it's generated by like, anything coprime, right? But one's always coprime, so might as well just say 1, right? I mean, for example, like Z mod, let's say 6Z, right? This is generated by 1. It's also generated by anything coprime to it. I guess, 5. Yeah. Or let me just say, or. Right? If you don't believe me, let's try it. 5 to the 0 is 5. Oh, sorry. 5 to the 0 is just, let's just do 5 to the 1. This is finite. 5 to the 1 is 5. 5 squared. The operation is plus, right? As a group. So this is under plus. So this is 5 plus 5. That's 10. 10 mod 6 is 4, right? 5 cubed is 5 plus 5 plus 5, right? We know 5 plus 5 is 4. So, and 9 mod 6 is 3. So hopefully you can see 5 to the 4th is just 3 plus 5, right? Because 5 cubed is 3. That's 8. That's 2. Yeah. And then 5 to the 5th is 2 plus 5. And then that's 7, and that is 1, right? And finally, we get back, we get to 0, I think. So 5 to the 6 is 1 plus 5, and that's 6, and that's 0. Yeah. But if you don't like this, you can always say it's generated by 1, right? 1 plus 1 is 2, 1 plus 1 plus 1 is 3, so on and so forth. Okay. So now that you understand this, let's ask the question, right? Define phi from Z mod 3Z to Z mod 9Z. From that sends 1 to 1. Is phi a group homomorphism? So here's my first question, right? To define a map from Z mod 3Z to Z mod 9Z, I need to tell you at least where every element goes, right? So I'm telling you right now, it's enough to just say 1 goes to 1. Why? Because where does, so just from this, ignore the question, where does 2 go? I guess to be precise, let's put a 3 and this is 9. Yeah. So this means mod 3, this means mod 9. So where does this go? So let's use this thing again, right? The beauty of being a homomorphism. Yeah. So phi of 2 is just phi of 1 plus 1. Do you all agree? And using the property, this is just phi of 1 plus phi of 1, right? Using this. Now, I know what phi of 1 is it's this. So it must be 2, 9. 2 mod 9. Do you all see this? Yes or no? Okay, so this is okay. So now what you're going to know is this is the problem with defining a map. Let me just say the answer to this is not well defined. I'll sort of explain what this means. But let me just tell you, like, where does 3 go? Just from this, this thing right here, right? Like 3, you're gonna see it goes to 3, 9, right? Everyone agree? But what is 3 in Z mod 3Z? 0, right? And let me ask you, we just went over this. What for to be a group homomorphism, what must 0 go to? Yeah, 0 must go to the 0 mod 9, right? So you see there's a problem here. And the issue is it's not well defined. So whenever you define something from, like, when you mod out something, in this case you mod out by 3Z, you always have to check it's well defined. In other words, it's independent of the class, right? So if you remember, like, the class of 1, you could choose a different representative, right? You could choose 4 or 7, right? All of these are possible choices, right? Because all of them have remainder 1 when dividing by 3. Do you all see that? Right? So similarly, 0, right, is the same as 3, is the same as 6, right? So it shouldn't be that this thing maps to one thing and then this thing maps to another. Yeah, that's what we call well-defined. So, like, not well-defined. So to be well-defined, like, it shouldn't depend on the class you choose, right? Because these are just the same things in Zmod 3Z, right? But it should be independent of whichever representative you choose, right? So yeah, that's the issue here. It's because 0 doesn't go to 0. Okay, everyone good so far? So this is the nice thing about being cyclic, right? Zmod 3Z is generated by 1. Do you all see this? And for cyclic groups, all you have to do is tell me where the generator goes, right? Because if powers of 1 generate it, this property right here tells me where every other element goes to, right? Like 2 must go to this thing, right? 3 must go to, so on and so forth. So that's the nice thing about cyclic groups. You know, just by saying where the generator goes, if it is a group homomorphism, you know where every other element goes. Just from, like, this property right here.
Matthew.
Yeah.
So it can't be a homomorphism if it's not well defined, right?
Yeah, it's not a well-defined map. Yeah, it can't be because remember, to be a group homomorphism, you must map 0 to 0, right?
Oh,
These
okay.
two are these two are not equal.
Thank you.
Yeah. Okay, so let me go over one just to give a brief because I don't see you Friday, and so let me just give you a brief introduction to zero divisors, and then we'll call it a day. Zero divisors. So let me just say normally, if a times b is 0, then a equals 0 or b equals 0. Do you all see this as normal? Like, does it seem obvious to you? Like, I mean, obviously, if I say normally, it's not always true, right? But hopefully, you see, like, at least for integers and rational numbers, this is true, right? If you multiply like two non-zero things, you're not going to get a zero thing, right? So let me just say this is not the case in some rings, right? So a zero divisor is basically a times b is 0, but a, b not equal to 0. So both of them are not 0, but they multiply to 0. And you see there are examples now, right? Like z mod nz for n not prime. Yeah. So I mean sub example like z mod 6z, right? 2 times 3 is 6, which is 0. Yeah. But these two are not 0. Right? Like 4 times 3 is 12, which is 0, because it's divisible by 6. But none of these are 0. Right? And then you have like another example like matrices, right? Matrices, you see tons of them, like M2 2x2s, where an example would be something like, I don't know, 1 0 0 0 0 0 0 1, right? If you multiply this, you're gonna get 0. I guess in this case the 0 matrix, right? But none of these are 0. So that's what zero divisors are. And the reason you're gonna learn it on maybe Friday, I guess, but I'm just giving you an intro. So the reason we don't like this is because we don't like this. Obviously, it makes stuff confusing, right? We don't like this, but also because let me just say because hard to determine number of solutions to polynomial equations. So let me just ask you one question. X squared equals 1. How many solutions does this have? Like, let's say over real numbers or complex numbers, if you like. Not a trick question. 2, yeah. Yeah, 1 and minus 1, right? So here, right, these are nice because then part of the reason is R has no zero divisors, right? When you multiply two things and you get 0, one of them has to be 0. But you see, it comes the issue like over like z mod 8z. Like x squared equals 1 has 4 solutions. Right? Like there's 1 squared is 1. 3 squared is 9. 9 mod 8 is 1. 5 squared is 25. 25 mod 8 is 1. 7 squared equals 49. 49 mod 8 is also 1. So normally you want to say a polynomial of degree n has at most n solutions, right? Like if I have a polynomial of degree 3, there should be at most 3 roots, right? It's not the case here. Like this is degree 2 and it has 4 roots. you see like that. So like we don't really like we don't really like things with zero divisors, so that's why we go over them. Yeah. Okay. That's all I have for today. Good luck on your quiz, and I'll see you next week, Tuesday.
Hey, Matthew.
Yeah.
For cyclic groups, the example where it was not well defined, is this true in general for like if it was mod 4 to mod 10 or whatever?
There are cases where it is, right? So if instead I map, let me just go next. If instead I map like this is fine now. because you know 9 goes to 9 mod 9 goes to 9 mod 3, but 9 mod 3 is 0. Yeah.
Right. Okay.
So there are cases where it's well defined, but but I mean but I prefer to give you one that's not, so you see it. So like yeah, so I swapped it.
Okay. Would the general rule then be if it's going from a smaller group to a bigger group, it's not homomorphism?
So no. Try this. (11 mod 11 gets mapped to 11 mod 5, but this is not 0, right? This is 1, right?
Right.
So this is not well defined.
Okay.
Yeah, you just have to check. Like, sorry, I always get commercial phone calls, but yeah, you just have to check. Case by case.
Okay. Thank you.
Good.
Lunch.
Okay. Anyone else? Any question? Okay. See you.